Chetan Prakash received his doctorate in mathematical physics from Cornell University and is professor of mathematics at California State University, San Bernardino, and director of the Center for the Study of Consciousness. He has a number of scholarly publications, and one of his aims in his research is to elaborate a theory that shows that how consciousness can give rise to the physical world as our interface with reality. Professor Prakash is also a senior 6th degree black belt instructor in Aikido, and his talk will be about interface theory of perception and conscious reality.
Thank you very much. Thank you. Thank you. Thank you so much for inviting me, and thank you, Urban, for giving my talk. That was a wonderful encapsulation of so much that I guess the rest of us have to talk about. And I do apologize, I may have to sit a little bit while I'm doing this. Anyway, so the title is The Interface Theory of Perception in Conscious Realism, and I seem to have 2 slides in one. Yeah, okay. So I'm going to mention a few theorems on the invention of structure in the world, and most of my talk is going to be setting up these theorems and explaining them to you. So let me just launch into it. So in this talk I will show that evolution by natural selection entails that physicalism is false. Okay, so we've introduced death already, there'll be sex in a few minutes. That's for novels, it's important to have all these things together. So, what do I mean by that? Well, physicalist theories, everybody agrees that perception is construction, but a physicalist I'm defining as a person who believes that perception is reconstruction. In other words, the assumptions include the following. I think I have to sit down, sorry. Our perceptions estimate true properties of the physical world, okay? So there's an objectivity involved in that. Another assumption is that evolution guarantees that these estimates are accurate. This is dogma in perception science as far as I know, okay? Apparently it's not dogma in certain other areas, as we were discussing earlier on. But the idea is that evolution guarantees these estimates are reasonably accurate, and the more we evolve, the more accurate they will be, and there's a convergence towards objective reality. So, as a consequence of these assumptions, we have to say that physical objects have causal powers. And in particular, brain activity causes consciousness. Okay? So let's question these assumptions. I have to apologize for the first slide because it was meant to be a video and it didn't translate from Keynote to PDF or whatever. But the first assumption I want to question is whether perception is veridical or not. And there's a host of examples. The one over here is from Color from Motion, and this is actually a wrong picture, almost a wrong picture to give you. But what happens is that these blue dots, as they're going across the screen, you just have blue and black, and they're moving across the screen, and you get this field of blue that suddenly emerges because of the motion of these dots in between the dots. So right now there's not supposed to be any blue in between them, though there has been some leakage in the computer, but we will create that leakage ourselves. Sorry, I'll have to show it to you some other time. So the first one is whether perception is veridical or not, and I think there's a fair amount of evidence that it's not, though some people would argue that it's almost veridical. I'm not so sure about that. Does natural selection, which is generally agreed upon process for evolution, does it favor veridical perceptions? And so I just have 3 slides on it. I don't know if you've seen this before, but this is a famous example of how this can go wrong. Well, I don't want to dwell on that because that poor moose is suffering. Anyway, so I'm going to address these, and I'm going to argue against those assumptions by stating 3 theorems, and most of the time will be spent on the first one, which has already been mentioned by Urban, that triangle over there was a bunch of simulations that were done by Hoffman and his lab. And then later on, Hoffman asked me if I could prove something about it. And I said, let's give it a try. So now we actually have a theorem which is much stronger than a simulation. It takes a while to set it up. It's almost trivial to prove. So, but the theorem is that interface agents dominate under natural selection agents that see the truth. So if you remember that last triangle that Urban had up there, that is actually something which we can demonstrate has to happen. Where am I? Yes. Second theorem is, what I claim is that conscious agents impute a spatial structure to the world, and that's a structure that the world may not actually have. I'll try to be clear about the hypotheses that go into these theorems. And the third theorem is that conscious agents impute probabilistic structure to the world, structure that the world may not have. In other words, agents imagine, and perhaps for the sake of evolution and for fitness, certain structures that do not have to exist. Okay, so in order to motivate the first theorem, I'm going to introduce the notion of physicalist evolutionary theories. Okay, so physicalist evolutionary theories are about objectivity, that our perceptions have evolved as veridical representations of the objective world. And so I'm going to call a veridical perception one which is attuned to the given structure of the world, what we think of very often as physics, or the physical structure. Okay. In contradistinction to this, Don Hoffman introduced what he calls the interface evolutionary theory. Actually, that's what I call it, but he should have called it that. And that's that our perceptions have evolved as a user interface between us and an objective world. So that's why I have this desktop over here, where our perceptions exist on this desktop in some sense. It's an interface with the world that we're interacting with. And let's see, sorry, I keep clicking the wrong thing. Interface perceptions then are the ones that are attuned to evolutionary fitness, okay? So just to give another little break, here's an object, here's a being that finds that object very fit, here's a being that couldn't care less. All right, so of course, when I made this, I borrowed this slide from Don, and then I realized that actually there's a further problem, that now the lion is confused about whether to have fresh meat or not. But anyway, I'll move on from there. We're going to develop our mathematical models of perception, cognition, and hopefully consciousness based on some standard mathematical areas. The first of which is evolutionary game theory, which is the theory of replication, retention, selection. I think this is a quote from Dennett, if I remember right, that it's ontologically neutral. And so he introduced the word universal Darwinism, even though he has a very clear ontology for himself. But as he says, whether evolution has a purpose or not, it is the mechanism for the adaptation of a species to the world. Okay. The other theory that comes into play, because perceptions can be dispersive a little bit, is the probability theory and Bayesian inference. These are standard within perception science, at least. So theory of inference from uncertain evidence. And then I'll spend a few minutes talking about group theory and geometry, which is a theory of space-time symmetry and its breaking. So these are the ingredients that are going to go into this. So now I'd like to model some perceptual strategies and then run an evolutionary game between them and see which one wins. Okay, and there's a clear-cut mathematical formalism for doing so, involving what's called the replicator equation. I'm not going to bring up those slides because I realize that not all of you are that interested in the details, but I can certainly talk about that later. Okay, so the setup is that we have a set of world states W. I'm not saying what they are. At most, what I'm going to say is that it has the structure of a probability space. Okay, that's sort of the minimal assumption I have to make. Similarly, there's a perceptual space. that a conscious agent can have is the perceptual space, which also has the structure of a probability space. And an ideal perceptual strategy assigns a percept to each world state. So it's a function from world states to percepts, or you may even say qualia. Okay, and more generally, a perceptual strategy allows for dispersion. So it's actually what we call a Markovian kernel. It's a probability that the percept X will light up when the world is in the state W. Okay. Now I'm putting that in small print because I'm going to use the ideal observer for most of this work, though all of it can be transformed into the more general setting. At least not all of it, but most of it. But I want to be honest about the fact that these are Markovian kernels, not just straightforward functions. So fitness is going to be very simply modeled. Fitness function is a species-specific function assigning to each world state W a positive number, which is called its fitness. So that's a function from the world states into positive or non-negative numbers. Okay, you could have zero fitness. So veridical or truth strategies are computed as follows. First, you use Bayes' theorem to estimate for each possible percept X. Let's say it's in my eye. So for each percept X in my eye, a maximum a posteriori world state that could have given rise to it, and we call that world state W sub X. Okay? So now you look at all these world states associated to all the different perceptual possibilities, and you choose that percept X naught that maximizes the fitness of its maximum a priori state. So you're looking at the best possible fitness of the states that could have objectively given rise to the percepts that you could possibly get. So this is sort of like a resource game in which an animal is looking at the world and trying to find the place that will be fittest for itself, but using an objective notion of what the world is. So that's a veridical or a truth strategy. I just call it truth for short. And so that's just a formula that says that you're looking at the maximum of the MAP estimates. So the maximum of the fitnesses of the MAP estimates. Okay? Seems like a reasonable way to go if you believe in a real world. Now, I apologize about the sequencing, but I just want to point out that here's a picture of that. There's a world, there's a perceptual map, and there's a perceptual space. Okay? And for any particular point that lights up in your perceptual space, there's a set of world states that could have given rise to it. That's what I call the fiber over X, or P inverse X, if you like, if you prefer that terminology. And so now the fitness of this percept has to be given a definition, and it's the average of all the fitnesses of all the world states that could have given rise to it. Okay, so it's an average over the fiber. This is a computation, by the way, which also uses Bayes' theorem in a very simple way. So, interface strategies then, first compute the average fitness of each fiber over X. All the world states that could have given rise to your percept, that's the average fitness of those states is your fitness for your percept, and then it chooses the percept that maximizes the average fitness of its fiber. Okay. So we have two strategies, the truth strategies and the interface strategies, and the question is which strategy dominates. Okay, so the first theorem is that interface strategies dominate truth strategies. Not always. In fact, if you remember the triangular picture, there are certain configurations where truth may dominate over interface based on fitness. Both of them are based on fitness, both of them are based on Bayesian analysis in some sense. But for the vast majority of interface strategies, for the vast majority of situations where you have an a priori measure that is given, and you have a given perceptual map and so forth, and a given fitness function, for the vast majority, interface strategies will dominate. And specifically, it goes like this. Suppose you have a world, W, and a finite sensorium, X. Over all possible fitness functions and a priori probability measures on W, the probability that an interface perceptual strategy will dominate a veridical strategy is given by at least, is bounded below by this quantity, where the modulus of X is the size of your perceptual space. Now you can see that this quantity is going, as the size of your perceptual space gets more sophisticated, increases, and you get more sophisticated perceptions, that what this is going to do is the probability with which interface will dominate truth goes to 1. Okay? And this is generically in a priori measures and fitness functions. So specifically, these are the assumptions and this is the conclusion. If being attuned to fitness dominates being attuned to some structure, if indeed it exists in the world. I mean, this is a kind of reductio ad absurdum. I mean, we're assuming that there is a structure, then on the basis of that we're developing this. Okay? And we're seeing that even if there is a structure, it kind of gets obliterated. Well, at least the species that sees it gets obliterated. Okay, yes?
So in one direction, you took the maximum fitness in the fibers, if I understood you correctly, and
I found a maximum a priori world state that could have given rise to that particular percept.
yeah. But the fitness of the percept itself is the mean of
No. So then I look at the fitness of that maximum a priori percept. That's my best estimate of what in the world actually could have given rise to my percept. So that's one state of the world. That has a fitness. And then I look at all possible such results and then maximize that. That's the objective or truth observer. Whereas the other one is doing averaging. You know, it doesn't. Of course, it doesn't know. It doesn't bother to look for a maximum a priori estimate of what world state could have given rise to the percept. It just looks at all possible ones and says, okay, what's the average of that? I'll call that my fitness. So, and so there are these two animals which are roaming around in a region looking for food, and they have these two different types of strategies for what they see as food, and they'll go to the region where they have maximum fitness. So it's that kind of that's why I call it a resource allocation game, a resource strategy, sorry. That's better. Okay. So in that context, it's not hard to use the standard evolutionary game theory to come to this conclusion. And this is over, in evolutionary game theory, you have different results based on whether you have an infinite population or a finite population or a large finite population. This is pretty much for any of those situations. Okay. So the implication is that this is just one possible implication, is that our physical vocabulary, as an extension of our perceptual predicate vocabulary, something went wrong. Oh yeah, sorry, our physical vocabulary is an extension of our perceptual predicate vocabulary, and so is the wrong vocabulary for the causal structure of the world, based on this particular result. Okay. So there are various objections to this domination theorem. In view of the time, I realized I may have too many slides, so I'm just going to flash these. In perception science, people have a notion of homomorphism, which means that basically your fitness should correspond to the structure of the world. But of course, it's species specific. So, there's no reason to suppose that there should be a homomorphism. But I won't get into that any further right now. Maybe afterwards we can talk about it. There's a quote from Bertrand Russell, which he concluded that it would seem that wherever we infer from perceptions, it is only structure that we can validly infer. And I'm sure that he was thinking about an objective structure in the world. I can't say, I'm not an expert, I'm not a philosopher, and I don't know that much about good old Bertrand. But what I want to point out about this is that, yes, maybe that is what we can validly infer, but it may not be the structure of the world. It's the structure which is existing on our interface. Okay. Oh, wrong one. Okay. Another objection to the domination theorem, or the consequence of it, which is that we should probably not believe in the ordinary physical causal structure of the world, is that there is consistent agreement amongst all of us on things like 3D shapes and textures and so forth. And so how can you say these are fictions of our interface? Well, that brings me to the fact that even though these are very strong intuitions, they're dead false if my theorem is correct. And the theorem which I'll be talking about in a few minutes, how much time do I have?
A little bit more than 10 minutes.
Okay, so I'm going to go through this part a little bit more rapidly then, thank you. But I can summarize it by saying that an agent can see space, or space-time perhaps, which I won't talk about right here, but as a property of the world, whether the world actually has that structure or not. And this is just sort of a logical conclusion. Okay, so before I get to that theorem, I want to conclude this part by talking about what is meant by the interface theory of perception. Essentially, we see space-time and the arena for the physical world as our desktop or as our interface. Physical objects then are icons on that interface. Okay, and they are icons that our species has constructed over billions of years. Icons seem to interact via physical law, but physical causality by itself has to be a fiction because objects are icons. Icons do not cause or have a causative effect on other icons. Okay, so
with icons you mean symbols?
Symbols, yeah. I'm using icon as in a metaphorical way. Yeah, yeah. So they're symbols, or they're. I'm not no expert on this, but yeah, they're symbols. And so you may object that you shouldn't, if a train coming down the track is just an icon, why don't you just stand in front of it? But I take my icons very literally. I don't take them seriously as necessarily representing something behind what I'm seeing, but I do take them seriously. Don's example is if I have a thesis lying on my desktop, I don't just drop it in the trash. Something bad is going to happen. It may not be happening in the real world, but it's certainly never available to me after that. So I do take them seriously. Oops. And so that kind of puts the mind-body problem a little bit on its head. And I'll talk more about that a little bit later. So here's my question. If evolution favors interfaces as perceptual strategies, and if space-time is a species-dependent construction, so what I'm claiming is that different species have different space-times. And in fact, perhaps there's a lot of variation between us also, but much less than across species. But if that's the case, then this invites us to start out anew in developing a model of consciousness, because it's consciousness that's doing all this. It's interacting via its interface and so forth. So there are other reasons. I would say that for many decades now, neuroscience has developed a rich and multifaceted study of neural correlates of consciousness, but has not produced any clear-cut mechanism by which neurons produce consciousness. I mean, correlates are one thing, but that doesn't automatically, we automatically assume our brains must create consciousness, but why? We have no reason to think so. We know that brains are very, very important for consciousness, at least for our waking consciousness, or living consciousness. If I lose my brain, I'm no longer conscious. But what we don't know is that there could be many, many other consciousnesses in the process. So whether you buy this idea or not, oops, I'm an Apple guy, so I completely mess up sometimes. Okay, I'm going to make some proposals about consciousness that I'm not claiming are necessarily true, but I think it's well worth our time to think about developing a theory of how consciousness could give rise to the physical world as we see it. Okay, so what would that theory be? And here's a proposal for how we can start off, and this is really the beginning of a program that we are on, and we'd love to have more people get on it. So a conscious agent interacts with its world. What's an agent? And there'll be echoes of many of the things that Urban and other people have been saying throughout this. So we define a conscious agent as something that has experiences, okay, which lead to actions. As a result of experiences, we act, or an agent acts. And what does it act on? It acts on a world. And the world, of course, gives rise to experiences. So there's this triangle. And we'd also like to define, we call them X, G, and W now. We just use symbols for that. But we'd like to define how these processes happen. So there's a thing called P, which I've already introduced before, the perceptual map. There's a decision map, which I'll call a kernel later on, which takes percepts and makes decisions about actions. And then there are the actions themselves. Okay? So in addition to that, there's a counter or a clock that clicks every time there is an experience. You can decide where it clicks. We usually say when there's a decision made, it clicks. You have to just pick one. And so a conscious agent is a 7-tuple. Okay. An ideal conscious agent, these things are just, the P, D, and A are just functions. But more generally, they will be, these spaces are probability spaces. N is an integer, and the P, D, and A are Markovian kernels because this allows us to introduce uncertainty into the model. Okay, it's sort of the minimal assumptions that we think we can make. Now you might, I'm very intrigued by alternative systems of logic and probability, and this subject is open to being studied by those means too. So I think I'm just going to run through this very quickly. Those of you who understand what this is will understand. Basically, this is saying that each of these kernels takes the previous state, and on the basis of the previous, this is contextual. So on the basis of the previous state of the world, for example, in the very first one of these, a given percept gives rise to a probability on the perceptual space. I'm sorry, I said that badly. Given a previous percept, the current state of the world will give you a probability measure on your perceptual state. And so on and so forth. Okay? So conscious agent is the 7-tuple, and here's the conscious agent thesis, that every conscious entity and its activity can be modeled by conscious agents. If we've been sufficiently minimal with this model, then that will be true, but of course it's falsifiable. Okay, so I promise I probably only have 5 minutes, right? So I'll go through this very quickly because I want to talk a little bit more about where we want to go with this stuff. Okay, so there's this other theorem about space or space-time. Space, mathematically, a space is a G-set. It's a space on which a group acts. Okay, so you have various types of space. You have, for example, the three-dimensional space of Euclidean space, so you can have Minkowski space. That all depends on what the set is and what the group that's acting on that set. So just take this very gently, this slide. There is a clear definition of a space, and basically the invention of space theorem says the following thing, and this echoes I think some of the things you were saying about Heinz von Forster earlier on, which is that if a conscious agent's actions form a group, they're a group by themselves, they have a group structure. And if that agent's perceptions are tuned to its actions, which means that it's a G-set for that group, but the actions are not acting on the perceptual space, they're acting on the world. And the way in which they act on the world need not be a group action at all. But if the perceptions and the actions are somehow tuned, and you could say the world is amenable to it, which really says very little about the world itself. It just says that the world has to have enough points in it. Then the agent will see a geometrical space. It'll see space. And imagine that space, it'll see space on its desktop. Okay, so in that sense, it invents space. And I'm not going to go through all this. This is this formal statement of the theorem. The observer sees a spatial structure in the world given by its own symmetry group. But it is the agent that has this structure. The world may not have it. Okay? And the next theorem is the invention of probabilistic structures. And again, it actually is, it's a simple idea. It's the same sort of thing. I won't even state the theorem, sorry about that. Except for the last line, the agent sees a probabilistic structure in the world even if the world doesn't have this structure. It doesn't have to have a probabilistic structure. The probabilistic structure of the perceptual space, the action space, and the decision kernel between them is enough as long as the other kernels behave properly. So it can be defined completely within the agent itself. And it can impute a structure on the space. Okay, so the traditional mind-body problem is that the physical world is fundamental and gives rise to consciousness. We propose a reverse mind-body problem. Consciousness, and it's probably a much harder problem, I don't know. So consciousness is fundamental, and the conscious realism is the thesis that the world consists of conscious agents. That is, the entire world is that of conscious agents, and it sort of it connects a little bit with your talk yesterday, where you replace the word conscious with cognitive, which might be a safer word for me to use in the future. Okay, so this is, of course, a falsifiable thesis, just like all others are. Very quickly, where do we go from here? We want to know about the dynamics of conscious agents. When you put these things together, in other words, you could replace the world with another conscious agent. And so now you have two conscious agents, which are in a circuit together, or you could have a whole network of conscious agents in a circuit together. Essentially, the world can be thought of as another conscious agent. And it could have the structure of a network of conscious agents. So you develop a dynamics of conscious agents, and what we'd like to be able to do is to study this dynamics to see how it can produce, how you can identify higher level conscious agents, to see what the asymptotics of this dynamics are, to see what kind of combinations evolve. And there's a thing in philosophy called the combination problem. This would solve it. Okay. We'd also like to build circuits of conscious agents and explore their properties. We've actually published papers in review right now where we are making a start towards discussing circuits and so on, including things like memory, predictive coding, and so forth. And we'd like to show how spacetimes emerge as efficient coding schemes from the interaction of conscious agents. That's actually what I'm working on right now. This is not an idea that's just come from us. Apparently it's quite big in the physics community. And anyway, I'll just leave it at that and say, so what I'm really working on right now is to see how this huge information space that the conscious agents create can be compressed into geometric algebra, which, in other words, using symmetries to be able to then objectify, to be able to make an objective world. Okay. Is quantum theory natural? You talked about that earlier. We have some dynamics in which the asymptotic behavior is very reminiscent of a free particle. So that doesn't mean anything, but it's a clue. Okay. Yes, let me save some time for some questions, please. Thank you. This is actually almost the end of it, so I'll just leave it without saying what it is. Thank you very much.
Can you go back to the scheme where you have the world and
There must be some way to do this, which is...
Sure.
So pardon? This one? Okay. This one?
Yeah.
Ah, oops. This would exist even if I went up to here, right? No, doesn't. Okay. No, no. Yeah, well, while you're asking the question, I can.
So it's a question that relates also to the previous talk, where
You speak a little louder.
so it is a question related also to the previous talk, and I'm a little bit confused by the perspective you have. If you have this world outside, then you have some agent,
Mm-hmm.
and then you have this mathematical representation of what's going on. Now, also in relation to the previous talk, where there was a discussion, a relation between Husserl and Serres. So Husserl takes a neo-Kantian perspective, of course, in which there is a representation. So there is a difference between the empirical subject and the transcendental subject. So there is a representational scheme where there are categories that allow us to grasp what an object is. So an object is not something that is self-evident given, as in the case of empiricism, for example, in the sense that I just see this mobile phone, this is completely unproblematic. And then I provide a mathematical scheme that allows me to discuss about this mobile phone, which I don't know how you can do without the notion of object, which is what Husserl is talking about. Now, Husserl tries to go from the empirical subject into the transcendental subject, or at least from the kind of introspection into the categories that allow us to speak about the world. Now, in that scheme, I don't see where the representation is.
The representation of objects is in X.
So you're not talking about a subject. I mean, you're not talking about an individual agent.
Yes, this needs to model an individual agent as well as this could have much further structure within it.
But that already has a structure.
It has the structure of a set with yeah.
So you have a mathematical structure, you have a categorical structure. But if you have a categorical structure, then you already know what the world is like, because you are already categorizing the world.
We just know that it's a set. The best we can model it is as a set of world states. Now, this may not be true, but what could also happen is that the world W could be a collection of these agents too. In other words, you could have a situation that looks like this. X1, G1, X2, G2. And this itself could be much, much richer. You can plug any number of these things inside here.
So the world is just the world that we see, right?
No, the world is what we're interacting with. We are interacting with something.
So we don't know what the world is.
No.
Okay.
We're imagining in this model that it has states.
What?
We're imagining in this model that there is a world.
Okay. So
We're not denying the existence of some objective
It's a
world.
kind of X.
That's W.
Well, it's a W. It's a kind of unknown world, and the X
Is my perceptual space. That's my interface. That is where I objectify. I see objects. I see, I see the Fokker-Planck equation happening in there. That kind of stuff.
Sorry, just want to interject. Is the interface part of the world or is it part of me?
It's part of me
End of the world.
and of the world. Yeah. This is a little difficulty with. It's always going to be a difficulty with the model because I'm in the world, of course.
Right.
Yeah. That's why I say that the world can be thought of. We can model it as the rest of. It's a conscious agent itself.
Yeah, but then you get an infinite regression of conscious agent.
Yeah, it could be, or it could be a very, very rich network of conscious agents.
Last question there.
Which is really what I think.
Yeah. It's more a comment because I think we need to discuss this further in more detail, but this reminds me strongly of an approach started by the psychoanalyst Bernardino, which is called the psychoanalytic ontology of action.
What is his name?
Turchin. I have been continuing that after the death of Turchin. I call it simply the ontology of action, leading to what I call radical non-dualism, which starts from an agent that has perceptions and performs actions. And out of the actions you can reconstruct the world, and it is everything is based on actions and agents. And consciousness, if you wish, is distributed through the world.
Yes.
And you can build more complex agents. It's a composition problem from psychism out of simpler agents by using that. It's like art for yes. If you have a network of agents that produce each other, you get a more complex agent that can have memory and other things.
I think that sounds very much the same thing. In fact, you may notice that the percept for the first agent is the action of the other agent.
Exactly, yeah.
Sorry, we don't have enough. You may ask directly to Professor Prakash.
Thank you very much.
Very much.